Hello and welcome to another lesson on A-level physics. Today's learning intention is to understand the significance of centre of mass. Today's success criteria is to be able to recall the principle of moments, to recall the definition of centre of mass, and to determine the centre of mass of an irregular object by a practical method. So let's start off by recapping some Turner effects. If you didn't do triple physics, it's likely that this is going to be the first occasion in which you've met the idea of turning and rotation effects with forces. So whenever you use a lever or a spanner, you are using a force to turn an object about a pivot. So if you take the example of that spanner turning the nut there, the centre of the nut will be the pivot about which the nut is being turned by the spanner. The longer the spanner, the less force will be required to loosen the nut, and that is because of how a moment is calculated. Now we calculate moment by multiplying the force applied by the perpendicular distance from the line of action of the force to the pivot. By line of action, what we essentially mean is an imaginary line directed in the direction of the arrow. So you can see the force here acting downwards, showing you with the cursor. This entire line here, shown by the cursor, would be the line of action of the force. And obviously the distance that has been labelled is perpendicular to the line I'm making with the cursor. So moment is force multiplied by perpendicular distance from the line of action of the force to the pivot point. The pivot point, of course, is the point where the rotation happens around. So this beam here will be rotating anti-clockwise because of the force applied to it. So let's consider the units then. Force we know already is measured in newtons, and perpendicular distance is measured in meters. So therefore the units of moment are going to be Newton meters. Now we come to an important principle which is called the principle of moments, and that states that in equilibrium the sum of the clockwise moments is equal to the sum of the anti-clockwise moments. This comes up often as a recall problem on the A-level physics exam paper for 2 marks. What this essentially means is that if we are in equilibrium, the sum of the clockwise moments is equal to the sum of the anti-clockwise moments. Equilibrium, of course, meaning that there's going to be no movement, no turning effect at all. The object is balanced, essentially. So let's look at an example problem then. A uniform plank of wood of weight 98 newtons and length 5 metres is pivoted over its 2 metre point as shown below. It is held in equilibrium by a rope, and we've been asked to find the tension of the rope. So, to begin with then, we need to consider where the forces are acting on this plank of wood. Well, the rope is going to be acting 2 metres away from the support force, but there is going to be another force acting on it as well from the centre of the wood. Because it is uniform, we can assume that the weight of the wood acts from its centre. Now we can work out how far away the pivot or the support is from the centre, because if we know that the whole thing is 5 metres long, then that means that the distance C to B will be 3 metres, and so the distance from C to the centre of the wood will be 0.5 metres. Now the weight, we just said, acts from the centre, and the tension is acting from the end, and we are holding the uniform plank of wood in place there. Now the principle of moments tells us that in the equilibrium which we're in, the total anti-clockwise moments have to equal the total clockwise moments. Now the force that is going to make this plank of wood go anti-clockwise would of course be the tension, because that would pull the left hand side down and raise the right hand side. So that moment would be calculated by the perpendicular distance 2 multiplied by the tension T, and that has to equal the clockwise moment, which is being caused by the weight of the wood. The weight of the wood is 98 newtons, and we would multiply that by the perpendicular distance from the support, which is 0.5 metres. And so by taking moments about the pivot, we can say that 2 times T is equal to 0.5 times 98. So when we divide both sides of the equation by 2, we would find that the tension needed to hold that plank of wood in place would be 24.5 newtons. Let's have a look at a second and more complicated example. We've been asked to find the size of the force exerted by the biceps in holding this bag of gold still. The bag of gold weighs 100 newtons and the forearm weighs 20 newtons. Now this is more like what will come up in the exam because there's more forces involved. There's actually 3 forces here. We've got the weight of the gold, the weight of the forearm, and then the force caused by the biceps, which they've called the effort force. Now I don't like that diagram, and I would find it much more easy if I could see a simpler diagram that just showed the forces and the distance. So I'm going to redraw that first of all as shown here, with the effort force being 0.04 metres away from the elbow, the weight of the forearm being 0.2 metres away from the elbow, and the weight of the gold being 0.4 metres from the elbow. Now I've done all the distances from the elbow because the elbow is going to be the pivot point about which all the rotation would happen. So now it's a case of applying the principle of moments. So I can say that by taking moments about the elbow, the sum of the anti-clockwise moments has to equal the sum of the clockwise moments. Now the forces that are going to cause an anti-clockwise motion in this case, it'll be the weight of the gold and the weight of the forearm because they would pull the arm downwards and thus anti-clockwise. So the moment caused by the weight of the gold would be 100 times 0.4, and I would add to that the moment caused by the weight of the forearm, 20 times 0.2. That has to equal, to be held stationary, that has to equal the moment caused by the effort, which is, I will call it E times 0.04. So simplifying that, I would find that 44 is equal to 0.04 E. So the effort force will come out as 1,100 newtons needed to hold that bag of gold in place. Okay, now we'll come on to another definition. The centre of mass of a body is the point through which a single force on the body has no turning effect. So essentially, if you applied force at that position, yes, you might move the object or the body, but there would be no rotation happen whatsoever. Now, the centre of mass is important because in effect, it is the point where we consider the weight of the body to act when studying the effects of forces on the body. So we will always be drawing our weight force acting from the centre of mass. Please, though, in the exam, when asked for the definition of centre of mass, you must say that it is the point through which a single force on the body causes no turning effect. Now, for a uniform shape, the centre of mass will be along its line of symmetry and will be found at the centre of the object. So if you draw 2 lines of symmetry on the object, you will find that where they intersect will be the centre of mass. But that is for a nice uniform shape. Not all shapes are uniform, as you can see by this thin irregular sheet of material here. In this instance, we would need to do a practical investigation to determine where the centre of mass would be. To do that, what we would do is we would suspend the object from a pin so that it is freely suspended and able to rotate. Now, when this object comes to rest, it will do so with the centre of mass directly below the pivot so that there is no resultant moment. Then we would suspend the same irregular object from a different position, again making sure that it is freely suspended. And now where the 2 lines that we draw on the card intersect with each other, that will be where the centre of mass is located. And you can do this yourself as a practical investigation on a piece of card.